In this short presentation, we review the results published in The Origin of Mass and the Nature of Gravity paper, where we demonstrate that the electromagnetic quantum vacuum fluctuations dynamic of space-time at the Planck scale is the source of mass, the strong interaction, and the gravitational force. We will detail how Max Planck, from the study of the black body radiation, found that the ground state of the oscillator internal energy predicts a zero-point energy, leading to the Planck's law solving the UV catastrophe. Although a common approach is to normalize the oscillator's Hamiltonian so that all ground state modes cancel out, setting artificially the zero-point energy to zero. However, zero-point energy is essential for the mathematical consistency of quantum mechanics, as it maintains the non-commutativity of the creation and annihilation operators, which results in the Heisenberg uncertainty principle and maintain the oscillator from dampening. In addition, from the consideration of the total energy density spectrum, we demonstrate that space-time dynamics is the result of the electromagnetic vacuum fluctuation energy density and then recover general relativity. We reconcile these quantum and space-time views of the structure of space and demonstrate that mass energy is an emergent property of space-time at the quantum level that unifies gravity and nuclear confinement under one mechanism driven by quantum vacuum fluctuations. Zero-point energy was discovered from the study of the interaction between electromagnetic waves and condensed matter, examining the photoelectric effect and the thermodynamics of black body radiation. Zero-point energy was first obtained by Max Planck trying to solve the UV catastrophe, where the ultraviolet emission diverges to infinity, present in the formal classical models as the Rayleigh jeans and Wien models, describing the energy density spectrum radiated by a black body observed by Kirchhoff in 1860. These early attempts at computing the energy emission spectrum of a black body led to the derivation of the Planck's law, giving the radiative energy surface density as a function of the massive body temperature and the frequency. The objective was to understand, from a thermodynamics point of view, the mechanisms of absorption and radiation of electromagnetic frequency of a black body held at a consistent temperature, and after the integration on all modes of emission, recover the Stefan-Boltzmann law. From the early explorations of thermodynamics and characterization of black body radiation, Max Planck predicted the existence of a non-zero expectation value for the electromagnetic quantum vacuum energy, or zero-point energy. From the mechanics of a quantum oscillator, Planck derived the black body spectrum, which satisfied the Stefan-Boltzmann law with a non-vanishing term remaining, where the summation of all modes of oscillations diverged to infinity in each point of the field. He then derived an expression for the internal energy in which appears a second term. This equation satisfies the equal partition theorem, but this new term meant as well that even at 0 Kelvin, oscillations still occur, resulting in what Planck coined zero-point energy corresponding to a ground state energy. At that time, zero-point energy did not appear in Planck's law for the energy density spectrum, although in modern course textbooks the zero-point energy density spectrum is considered for the free field or vacuum. In 1916, Walther Nernst replaced the thermal term in Rayleigh jeans distribution by the frequency energy to estimate the zero-point energy spectrum of the free electromagnetic field. To avoid the UV divergence of the energy density, he had to introduce a cutoff frequency and realize that the vacuum energy density was quite enormous, making extraordinary fluctuations in it to exert great actions. Although the oscillator is typically visualized as a linear oscillating spring, one must consider that the spring analogy is a 1D projection of a 3D rotational motion. A 3D representation is a more realistic and precise visualization of what is occurring in the real physical resonators under considerations, as for atoms. Zero-point energy can be and is commonly mathematically removed from the Hamiltonian by normal ordering procedure, but this does not mean that zero-point energy vanishes from the system. In fact, the non-zero value of the ground state mode results from the non-commutative relationship between operators creation and annihilation, and is essential for the mathematical consistency of quantum theory. This can be demonstrated when we consider a dipole model of the atom where the dipole length is represented by the abscisse coordinates. The resulting harmonic oscillator equation, which takes into account the radiation reaction field and the small dampening approximation, and the zero-point energy source, shows that a solution without zero-point energy would result in a rapid decline of the oscillator and the collapse of the dipole length. This is analogous to the case of the classical electron, in which it would radiate all its energy and fall on the nucleus. Thus, the zero-point energy is a source term necessary to the stability of matter, counterbalancing the radiative dampening of the dipole. In the small dampening approximation, we can calculate the mean over time value for the commutator. We show that zero-point energy is required to maintain the non-commutativity of the operators, which leads to the fact that the Heisenberg uncertainty principle emerges from the vacuum fluctuations. In fact, the vacuum fluctuations are expressed by the position and momentum standard deviations, which are computed from the number operator eigenvectors from which the Heisenberg principle is deduced. It then follows that the foundations of quantum mechanics and the uncertainty principle are firmly rooted in the dynamics of zero-point energy vacuum fluctuations that defines the bath or the field in which particles appear, evolve, and interact. Thus, contrary to popular belief, the uncertainty principle is a consequence, not the source, of zero-point energy. These electromagnetic vacuum fluctuations were investigated by John Archibald Wheeler, who studied their gravitational impact on the curvature of spacetime. Wheeler analyzed the phase of the Feynman-Huygens equation for a field that combines an Einstein-Hilbert action and an electromagnetic free field, such that the exponent phase is described by the Einstein-Hilbert action with the electromagnetic potential vector and the spacetime metrics. This led him to find that these fluctuations have qualitative and quantitative consequences at distances in the order of the Planck length, where the metric fluctuations are coherent enough. Therefore, the spacetime curvature due to vacuum fluctuations gives birth to creation and annihilation of virtual wormholes described by Wheeler having a charge of the order of the Planck charge, a mass of the order of the Planck mass, and a typical energy associated with zero-point energy. Then, Wheeler investigated the possibility that the mass and charge of elementary particles could be described from a quantum geometrodynamic point of view. This would mean that mass and charge of elementary particles, such as the electron, would result from a collective and coherent disturbance of vacuum fluctuations associated with the metric and gravitational fluctuations generated by the creation and annihilation of Planck-sized micro-wormholes. Therefore, Wheeler calculated the characteristic length scale at which spacetime metric variation can be observed as a response of vacuum electromagnetic fluctuations, recovering the Planck length as a natural cutoff at which spacetime folds onto itself, producing discrete spacetime bubbles, coined quantum foam. The modern derivation of the total energy spectrum utilizes correlation functions to compute the destructive and constructive interference of the electromagnetic quantum vacuum fluctuations. The non-zero vacuum energy density only arises in coherent or symmetrically ordered space and results from the summation of all elementary spherical harmonic oscillators, with ground state energy on all possible modes of the field. For three-dimensional spherical oscillators, the energy density resulting from the ground state energy of the rotational oscillations for continuous mode distribution results in a diverging vacuum energy density. However, the frequency corresponds to a wavelength scale at which the measurement is made. Yet the vacuum energy divergence only occurs when an infinite amount of scales is considered. Thus, spacetime that appears flat at a large scale is in fact extremely energetic and fluctuating at the small scale of the quantum world. Since Einstein's field equations demonstrate that all energy sources will curve spacetime, the tremendous amount of vacuum fluctuations energy should result in a highly curved spacetime geometry and strong gravitational action at the quantum scale. As demonstrated by Wheeler in his paper Quantum Geometrodynamics, the continuous process of creation-annihilation, creating continuous distortion of the spacetime metrics, occurs only at a very short distance scales, namely the Planck scale, where the spacetime metric is in phase with the electromagnetic vacuum fluctuations. The quantum vacuum fluctuations energy density is directly related to the correlation time delineating and characterizing a coherent state of constructive interferences between electromagnetic and spacetime metric fluctuations, which corresponds to a characteristic scale defined by the system effective time tau. Thus, it's possible to compute the system energy density by considering the electromagnetic vacuum fluctuations correlation time utilizing the correlation functions, or Green's functions, of blackbody radiation. A characteristic time yields the energy density, giving a complementary meaning to the cutoff wavelength and being directly related to the coherence of the vacuum fluctuations defining the energy levels of the system. Remarkably, when we consider a significant change of scale from the Planck scale, and we implement the characteristic time of the proton computed from the proton charge radius, we obtain the energy density of the rest mass of the proton. This proton time is consistent with the characteristic time of the strong nuclear force, typically given by the Rho-Meson lifetime of about 10 to the 24 seconds. We find that the corresponding energy for that scale resulting from the coherent behavior of the quantum vacuum fluctuations in the volume of a proton corresponds to the rest mass energy of the proton. This non-trivial result shows a clear origin of the mass energy of matter emerging from quantum vacuum fluctuations at the Planck scale, through a decoherence or screening mechanism that generates the proton rest mass, which constitutes the baryonic mass of the universe. The factor of 2 introduced into the equation represents the creation and annihilation cycle of the oscillations, reducing the characteristic energy of the system by a half. In contrast, the current standard mechanism to define the source of the rest mass of the proton usually requires the strong nuclear force contribution to make up the deficiency of the Higgs mechanism, which only predicts up to 5% of the proton mass. While, as we have just seen, the correlation functions of the quantum vacuum fluctuations at the characteristic length of the proton result in predicting 100% of the mass of the proton. Furthermore, we note that this result from the correlation functions relates to the charge radius of the proton not only to the rest mass, but as well to the reduced Compton wavelength, giving a direct relationship between the proton charge radius and the proton reduced Compton wavelength. Hideki Yukawa utilized for the effective radius of the residual strong force this reduced Compton wavelength, which is also significant in the screening process. When we evaluate the Casimir force inside a proton cavity, we obtain a pressure on the order of the measured pressure within a proton core. Significantly, this force is on the same order of magnitude as the strong interaction characterized by the measured quark-antiquark gluon flux tube snapping. Therefore, utilizing the correlation functions of the electromagnetic vacuum fluctuations and the Casimir force of a cavity with the characteristic length of the proton charge radius, we obtain both its total mass energy and the confinement force measured at that scale, defining a complete mechanism for the mass and confinement stability of matter. We now investigate the mechanism in which the vacuum energy density transits from its highly coherent phase within the proton core to a less coherent phase, generating the rest mass energy. We find that this discoherence mechanism can be expressed in terms of an electromagnetic screening of constructive and deconstructive interference resulting from the creation and annihilation operators of the vacuum structure at the Planck scale. Following Wheeler's quantum foam bubbles approach and exploring the foam-like geometry of the spacetime lattice at the Planck scale, we define an elementary oscillator or voxel utilized to describe the electromagnetic vacuum fluctuations. These voxels, coined Planck spherical unit, or PSU, of a diameter of the Planck length and Planck mass energy, are organized in a Planck plasma fluid similar to the quark-gluon plasma fluid dynamics often associated with the quark epoch of the early universe. We describe the granularity or discrete structure of this Planck plasma fluid with space-filling voxels of PSUs. We find that such space has an equivalent energy density of the quantum vacuum fluctuation. We note that the space-filling nature of this computation must be kept in the context of a dynamical foam of spherical bubbles appearing and disappearing as creation and annihilation cycles. This results in an interstitial space-filling symmetry. The first screening of the vacuum fluctuations energy density reduces the core vacuum pressure by dividing it by the pixelated surface horizon eta. Remarkably, this initial screening computation gives a result corresponding to the first exact solution to Einstein's field equations from a consideration of electromagnetic quantum vacuum fluctuations alone. Examining the relationship of the electromagnetic vacuum fluctuations between an enclosed volume and its surface screening parameter, we find a direct and non-trivial path to general relativity and spacetime. This is another remarkable result considering that only vacuum fluctuations at the quantum scale were considered with a surface screening mechanism that now clearly relates to the typical semi-permeable structure of the event horizon of a black hole given by the Schwarzschild solution. This result brings further insights into the relationship between the quantum electromagnetic field, the origin of mass energy required in Einstein field equations stretch energy tensor, and the gravitational spacetime manifold curvature at any scale. Keeping in mind that Einstein field equations are fluid dynamic equations, they can be expressed in their dimensionless form in order to evaluate the amplitude of the mechanics involved. As a result, we find the Planck length and the vacuum energy density as natural normalization factors for general relativity. Therefore, the vacuum energy density corresponds to the energy density required to produce a spacetime bubble curvature on the order of the Planck length, which is consistent with the Planck cutoff. In the classical approach, one would expect a black hole formation to be the result of an accretion of infalling material to a critical limit. However, our result demonstrates that black hole formation is the result of a natural spacetime behavior emerging from a state of coherence of the collective quantum vacuum fluctuation oscillators in a region of space. We note that this mechanism of black hole formation from coherent modes of vacuum energy may explain the latest observations of the James Webb Space Telescope finding supermassive black holes in the very early universe where star formation and accretion would not have been possible to produce them. We now apply this first screening mechanism at the reduced Compton radius lambda p and obtain an analog to the undressed mass or bare mass of the proton. Astonishingly and remarkably, the first screening mechanism at the quantum wavelength reveals an internal core black hole at the proton scale. Although the concept of particles being black holes or at least hosting singularities at their core might be shocking at first encounter, however, this idea was considered by Einstein and Rosen in 1935 and later by many others in string theory, including Leonard Susskind in 2004, stating one of the deepest lessons that we have learned over the past decade is that there is no fundamental difference between elementary particles and black holes. This is especially clear in string theory, where black holes are simply highly excited string states. Indeed, throughout the modern history of physics, significant literature explored this possibility as a result of the quantum structure of spacetime. Einstein and Rosen conceived what is now known as the Einstein-Rosen bridges, later coined wormholes by Wheeler in 1957, where in order for spacetime to retain continuity, particles would have to be bridges between regions of space. Also, one may consider that the density of quantum vacuum fluctuations in a region of space largely exceed the value required to obey the Schwarzschild condition of a black hole. Therefore, by consideration of quantum vacuum fluctuations, one can only conclude that particles must be the result of highly curved space in a quantum region. To evaluate the dynamics of vacuum fluctuations in the surrounding strong gravitational field of a black hole proton resulting from the first screening, we compute the energy radiated from the corresponding Hawking radiation. Assuming the Hawking radiation mechanism is somewhat correct, although it has not been directly verified experimentally, it would stand to reason that if our solution to the origin of mass undergoes a first decoherence phase transition at a black hole condition, that one could calculate the Hawking radiation resulting from it. Applying Stefan Boltzmann law for blackbody radiation, the radiated energy of the core proton black hole at the charge radius over the proton characteristic time at the Hawking temperature, we get the total radiated energy at the surface horizon. Considering the space between the quantum horizon and the charged radius surface filled with vacuum fluctuations acting as a superfluid, we have an isothermal process between these two surfaces. Hawking utilized Bekenstein's work on the black hole entropy to derive the Schwarzschild black hole entropy and got a relationship between the entropy and the temperature. For the proton black hole, we consider a pixelization of the black hole surface by the effective cross-section of Planck's spherical units. In fact, nature does not tile in squares. A more natural representation than the usual square tiling utilized by Bekenstein is the cross-section of a sphere. Tiling the quantum surface, we find the Hawking temperature and the Hawking radiation energy. The black body radiation mechanism results from the vacuum fluctuations pair produced at the quantum horizon, and when considering a hexagonal capacity packing factor for the tiling of the entropy of the system, it diffuses to the charged radius surface, generating the proton rest mass energy. We have shown from the above solution that a black hole, whether a proton or a cosmological black hole, emerges from the flow of quantum vacuum fluctuations or Planck plasma energy density. The outward flow undergoes a phase transition or shielding the semi-permeable horizon, which is a mechanism that can be associated with the process utilized by Hawking to obtain his black hole evaporation construct. We now calculate the life expectancy of such black hole irradiating its mass energy undergoing Hawking radiation, considering the internal source term or total interior energy of the black hole. The black hole interior vacuum energy is dissipated at a constant rate associated to a reduction of PSU and black hole interior size, from which we evaluate the total evaporation time. We find a proton black hole lifetime is extremely long, on the order of 10 to the 35 billion years, making proton energy structure perfectly stable over a very long period of time. Furthermore, since the estimated beginning of the universe, the proton would have decayed in infinitesimal energy consistent with an extremely stable system. From the black hole proton lifetime equation, it is also possible to evaluate the radius reduction of the proton black hole since the estimated beginning of the universe due to Hawking evaporation and the production of the proton rest mass. We find 7.54 times 10 to the minus 52 meters, a variation much smaller than a Planck length and thus totally negligible compared to our time scale. No measurable variations to the mass or the radius would be observable within the short span of the contemporaneous age estimate of the universe. Therefore, the proton energy structure is perfectly stable over very long periods of time. One can consider the continuing aggregation of self-gravitating islands of PSU oscillators forming scale relationships in the Planck plasma as it undergoes phase transitions from the event horizon into a less coherent phase carrying less energy. This mechanism of energy screening can be represented as self-gravitating oscillators curving space-time that encapsulate the internal energy, reducing the available effective energy in the decoherent phases. The smallest self-gravitating island of PSU verifies the Schwarzschild condition and reaches the limit of space-time elasticity, resulting in the smallest black hole having a Planck mass energy. These initial micro-black hole pixels emerged from primary state of PSU organization in vacuum, coined kernel 64. One should note the particularity of this first division of space by quantum vacuum fluctuations, which obeys the Schwarzschild condition. This results in a kernel in which the surface information is equivalent to the volume information. Between the Compton wavelength horizon and the charged radius surface of the proton, the Planck plasma flow transits from single PSU to kernel 64 aggregates. This aggregation mechanism gives us a deeper understanding of the second screening resulting from the proton rest mass. As an analogy, while the first screening of the Compton wavelength horizon can be thought as having a mesh of characteristic wavelengths in the order of Planck length diameter, the second screening has a larger mesh of the 4 Planck length diameter of a 64 aggregate. We then compute the second screening energy density and find the rest mass energy of the proton. The solution is equivalent to the tilling of the effective cross-section of a 64 kernel on the surface of the charge radius of the proton. The factor 1/2 earlier associated with the particle pairs creation and annihilation process and the correlation functions for blackbody radiation becomes clearer as it may be related to a Hawking-type radiation of the internal black hole source identified as the first screening, where one virtual particle of the vacuum pair creation falls inwards and the other is radiated outwards. The screening mechanism generates an energy density gradient from the vacuum fluctuations to proton rest mass. We now investigate this gradient as a pressure gradient in the Planck plasma flow, which generates forces at the nuclear level. We relate the energy density to a perfect fluid pressure through an equation of state as usually considered in general relativity to model of a homogeneous and isotropic universe. The computation of the pressure force experienced by Planck spherical units in the Planck plasma flow by the vacuum pressure is found to be the Planck force. As seen earlier, Einstein field equations can be expressed in a dimensionless form to evaluate the amplitude of the ground state energy or force involved, and thus can be written in terms of the Planck vacuum density or the Planck force. As a result, we find the Planck force as natural ground state force being the source of curvature for general relativity. From this analysis, the Planck force can be seen as a pressure force required to generate a surface horizon at the Planck scale against the rigid elasticity of spacetime. The Planck force is therefore the ground state force that experiences a screening mechanism throughout the hadronic horizons. We evaluate the pressure force produced by the vacuum density at scales in which measurements can be observed, such as the baryonic scale of the proton. Using the equation of state, we apply the first screening at the proton scale and find a force of the same amplitude as the confining force, with the proton structure corresponding to the snapping of gluon tubes resulting in quark-antiquark pair creations. Considering a second energy screening, we compute the pressure experienced by PSU in the rest mass energy region and get a value of 10 to the 34 Pascal, in agreement with the recent and astonishing measurements which exceeded in measuring the pressure experienced by quarks in the proton interior. This extremely high pressure is also found to be in the order of magnitude of the pressure within the core of a neutron star or a stellar-sized black hole. We then compute the resulting pressure force experienced by the fluid particle, namely the kernel 64, of the proton external region and recover the gravitational force between the two contiguous protons. In Table 1, we summarize the screening of the Planck force undergoing two screening phase transitions to eventually reduce to the Newtonian gravitational force. During these two screenings, we recover the measured quark-gluon confinement force with the color force, demonstrating that nuclear confinement and gravitational curvature are emergent properties of the quantum vacuum fluctuations fluid dynamics at the different horizons. Thus, mass and forces can be unified under one mechanism involving the decoherence of a fundamental ground state energy central to the thermodynamics of quantum mechanics. We note that the force ratio between the strong force and the Newtonian gravitational force corresponds to the well-known gravitational coupling constant relating the nuclear force strength to the apparently weak gravitational Newtonian interaction between two rest mass protons. The black hole proton mass energy produces the strong color confinement occurring at the first screening of the quantum vacuum fluctuations and the apparent weakness of the rest mass resulting from the second screening. It strongly suggests that the strong force is directly related to the curvature of spacetime at the hadronic scale by the energy density of the proton black hole phase. It underlines the fundamental nature of forces at the quantum scale as the pressure of Planck plasma flow eventually resulting in the Newtonian gravitational force at large distance. Utilizing a screening mechanism resulting from the flow through a semi-permeable surface, we obtained a correct approximation of the forces at the different horizons. However, this computation only gives us snapshots of force strengths at specific horizons, while these forces have a continuous influence beyond the horizons, resulting in a residual strong force necessary for the nuclear binding energy. To evaluate the forces between horizons, we can consider the construction of a gravitational force potential, phi g, providing a continuous solution for the screening mechanism. The first screening of the Planck force reduces the pressure in the order of gravitational coupling constant within the very short range between the reduced Compton wavelength and the charge radius of the proton. To evaluate the forces close to the proton black hole horizon, we consider this reduction in energy density resulting in a reduced pressure force as the source of the color confinement force and the residual strong force. To evaluate the energy diffusion through this highly curved spacetime region of the proton interior, we construct a Yukawa-type self-gravitating energy potential scaled by the gravitational coupling constant alpha g and the strong coupling constant alpha S. This general potential is constructed as a superposition of the three terms resulting from two screening mechanisms. The first term corresponds to the first screening of the ground state Planck force and is the solution of a screen-Poisson equation involving a source term corresponding to the energy flux of the proton black hole radiated energy. The second screening term represents the quark-antiquark interaction potential with a Yukawa-type potential of characteristic length, the reduced Compton radius. The last term corresponds to the Newtonian gravitational potential yielding the gravitational force between two proton rest masses. At the proton black hole horizon, the gravitational force and potential are ruled by the Planck force and Planck energy respectively, as the source of mass and forces. At the Compton wavelength, the first term of the potential dominates, and as the distance continues to increase toward the charge radius horizon, the force energy density reduces and eventually the second term is predominant, resulting in amplitude analog to the color force as obtained earlier. For larger distances, the third potential term dominates and corresponds to the classical Newtonian gravitational potential between two protons at rest mass. Color confinement force, residual strong force, and gravitational force deriving from the general gravitational potential, illustrating the two screening mechanisms from the Planck force ground state. The first screening starts at the Compton wavelength horizon. At the proton radius, we recover the measured color confinement force value of around 10 to the 4 Newton, and at the typical internucleon distance of 2.6 times the proton radius, we find the typical 48.4 Newton amplitude range of the residual strong force. From there, the screening mechanism reduces the force dramatically again as we compute the approximate strength of this force relative to the electrostatic repulsion between two protons. The equilibrium is reached at a distance of 2.6 times the proton radius, or 2.18 femtometer, which is the typical measured distance between two protons in alpha cluster, given between 1.9 and 2.4 femtometer and yielding to the residual strong force estimate of about 48.4 Newton. In the discussion section of the paper, we briefly discussed the generalization of the screening mechanism at the universal scale. By applying the screening mechanism of the vacuum fluctuations at the horizon of the universe determined by the Hubble constant chosen at a typical value of 67.4 km per second per megaparsec, we compute the universe density and find the exact measured critical density at current time. Thus, we identify the vacuum fluctuations energy density as the origin of not only baryonic matter but also the so-called dark matter and dark energy of the critical density of the universal scale. Furthermore, considering that a single screening of the vacuum fluctuations is equivalent to the Schwarzschild solution, it results that the observable universe obeys the Schwarzschild black hole condition. Notably, by considering the relationship of the universal scale screening mechanism to the proton scale, we find the quantum vacuum energy or information within a Compton proton volume is equivalent to the information or critical density of the universe. This represents a conceptual holographic model of the information energy, both relating the quantum scale to the cosmological scale through vacuum fluctuations with specific scaling factors. The entangled state of black hole hubs at different scale generates a wormhole network as described in the ER equals EPR conjecture. Furthermore, while the volume of a proton seems to hold an equivalence of information energy in terms of vacuum fluctuations as in the volume of our universe, the surface information of all protons is equivalent to the surface information of the universe pixelized by kernel 64. These last two computations suggest an intimate relationship between protons and the universe, and that the local holographic screening of a system has non-local relationships to other scales. This information network generates energy density gradients in the vacuum fluctuations across scales, producing masses and forces that we experience and measure both at the quantum scale and the cosmological scale. To summarize, we have demonstrated that the correlation functions of the electromagnetic quantum vacuum fluctuations which define the energy density based on constructive and destructive interferences, are at the origin of both the blackbody radiation and the vacuum energy density resulting in mass and forces. We have shown that a first screening mechanism of quantum vacuum fluctuations derived from the Planck scale discrete structure of a horizon recovers a direct analytical solution to Einstein's field equations in terms of the Schwarzschild solution at any scale, including the proton scale. This provides not only a deeper understanding of the quantum nature of spacetime producing gravitational curvature, but as well, when applied to the proton scale, a source of energy at the origin of mass and forces. We have demonstrated as well that the Hawking radiation at the core at the reduced Compton wavelength of the proton corresponds to the rest mass energy of the proton and is equivalent to a second screening of the vacuum energy density. The gravitational curvature at the reduced Compton wavelength of the proton core results in the Planck force at the horizon, which undergoes a Yukawa-type potential reduction. It generates the known measured values for the color confinement force, the residual strong force, the nuclear binding energy, and at larger range, the Newtonian gravitational force. The resulting unification of mass and forces derived from a Yukawa-type phase transition of multiple screening horizons and the dynamics of the vacuum fluctuations lead to a clear picture of the gravitational quantization of space. It generates pressures and energy gradients at the origin of the structure of matter, the resulting quantum confinement and gravitational forces, and the agglomeration of organized matter, from the Planck scale to the universal scale. This can represent an important step towards achieving a long-sought goal in physics, an analytical and fundamental solution to quantum gravity.